Okay, so I repeat again, please. This is from the calculation, from the last calculation with the running rx.sh, you are going to have this, okay? So this is the total energy of my structure, my slab. Stopping means that the calculation was, the relaxation was correct. And 2 means that it took only 2 iterations to get the ground state. If you don't get these values, please, you can check over here. So maybe somehow the operative system was doing something not correct. So it is here. What is this? And the outcard, this one. Please check this outcard. This is the file that we get the result. Just in case this is going, how do I know this? It's because if you run this rx.sh, that the last thing we run, look this, you save this outcar-surf.st. That is the last calculation. Well, what is this hyphen dollar sign surf? Is this, right? What is this? 2x2 L5V10, right? So is this file, please? So I open this outcar. What is this outcar? Side of face is after this. This is my file. Look this. So please, if you don't have these values, check these values. And besides, a good exercise to know from where with the values, and it's from here. You see, you go to the last part, and you get this. You go to the last. This is you see the last line, free energy of the ion electron system, energy without entropy, blah, blah, energy sigma to 0. This is the energy we get. That is the energy you should get, okay? So if you didn't get this, please get this value, you are going to copy this and paste it here. If you don't have this correctly, this generated this file, surf.sh plus just copy this value here. Copy this value and paste it here. See, it's exactly the same value. See? And that's it. Nothing else. That's simple. And by the way, this is stopping. From where it comes from this, the outcar.rx here. Look this. If you open this outcar.rx, you go to the last lines, you are going to find this. You see? Reach relaxation. Sorry. You get this one, right? This reach. Sorry, I don't know what's going on with this. You're going to get this, right? You see, reach require accuracy, the stopping structural energy minus. That is the outcome item. What is this? 2x2 L5V10 of Rx. So this is the formula. Right? It means that your relaxation was correct and so. As I mentioned before, before in the old days when mobile machine was possible to use, this calculation takes several hours like this, or like this. So it took several hours, maybe 4 or 5 hours. Right now we can do this in a couple of weeks inside of the teaching. So that's very nice how we work. Okay. So if everything is fine, please, we are going to start to get the, and look this, what all the file we have. We have the DOSCAR, you see this file, DOSCAR 2x2 L5V10. So we are going to analyze this data and so, okay? So please open your Mathematica, the data analysis we were developing, please. So we are going to start to develop, to analyze for instance, the surface energy, right? So let's analyze the surface energy. So let's do this, okay? So with the data we got, okay? Let's analyze this. Surface energy. So this will be that will be a subsection, the surface energy. Okay. So this will be a subsection, please, surface energy. So for this, surface energy for me is equal to this, but before I will start to run this, what is my data here? In my case, this is my data. Please upload this, run this. And now I'm going to download this
this file. So I'm going to take this import, right? The surf, the folder surface of that, right? I'm going to take only this or only the first and the second one, nothing else. Like this. That's the only thing I want to get. Okay. Okay, so I'm going to pause this here till. So as I mentioned, this the surface energy is the energy that you need to split or to cleave a bulk material, and you check what happened with the reconstruction. Okay. Therefore, first of all, we input this, so it means that what the value we have to use is this, right? So this is the value I'm going to use, right? So, and first of all, I need to get the surface energy. If you check the manual here, they give me this formula. You see, is 1/2A multiplied by the energy of the slab minus the total energy of silicon times the energy of a single atom of silicon minus the energy, the number of hydrogens times the energy of a single, right? The energy of a single atom of hydrogen, please, we take it, I'm not going to compute here, just I'm telling you, the energy of the hydrogen atom for a single atom, I take it from the H2 molecule, right? Why? Because that is the stable phase of hydrogen, right? That's just why I take this. And the value using the same function that I'm giving this. The value of a single atom of silicon is given by this value, but we complete that already. Look at the first sections of this. Okay. So like this, we have this. So let's complete this. So let's place the values also. Any questions here, please? Somebody? I'm going to pause this here. Okay, so how to get the area, please? So the area here, you see, I'm coming here and see the Concar file, the 2x2, this one. This file here, please. Check the Concar, this, the 2x2, this one. This file, open up, and you're going to see the lattice vectors. So since I need the lattice vector A and B, I need to know what is the surface spanned by this. So what is the surface spanned by these lattice vectors will be, since it is a square lattice, so it will be only the square of this value. So I'm going to copy this, and I say the area 2x2 is equal to this square. That's it. Okay. The energy of the silicon, according to our last calculation, the energy of the single atom of silicon was minus 5 point. We computed this from the section 2, I think. Section 2. Section 1, I think. The first calculation we did, remember that we did the isolated silicon atom for it, right? And the energy of hydrogen, I computed for you guys. So, okay, so it's to compute the energy of the relaxed hydrogen molecule divided by 2 will be this, minus 3.379. By the way, the energy of this, of the hydrogen atom, in this case of the hydrogen atom, it's just half the energy of the hydrogen molecule. It was using exactly the same cut-off energy we use for the silicon. Okay, you have to use the same cut-off energy for all the calculations to be consistent and not and to decrease the error. Okay, so there it is. So the number of silicon atoms, how many silicon atoms there are? There are 20 silicon atoms, see? 20 silicon atoms. And the number of hydrogen atoms, right, is equal to 8. That's it. We have this. So we have to compute 1/2A, 2 times A, 2x2, right? Multiply by the E of the slab, right? Minus number of silicon atoms times the energy of a single silicon atom minus number of hydrogen atoms times the energy of a single hydrogen atom, right? Right?
And this, the only thing we have to check this, the energy of the slab is this one, right? Is this S. And that's it. Okay? This is as you can see, okay, the energy is in electron volts per Armstrong's square. Okay, I'm going to pause here till everyone hears the same. Now I'm going to teach you how to analyze the density of states. I'm going to put those, only the those, not the partial density of silicon. 100 sulfates. Okay, so I'm going to stop here, and this will be a subsection. Okay, so we are going to analyze the density of states of this and to see what is the property, right? So so first of all, the input is equal to import, exactly as we did remember in the section of the density of the states. So we're going to import this surf. The only those carries have a bay. Okay. Comma, since there are many, I'm going to put table. That is the way how we can enter this. Okay. So we put table. So my DOS, remember this, I'm replicating this, is input 7, remember this 7 plus 300. Exactly the same as we did before. And I need only the first and the second one. That's it. Okay. And I need also the Fermi level. EF is equal to input 6, okay. There it is. Okay. I'm going to pause this still here. Before I start to analyze and to visualize the density of states, I'm going to open the file and to check what is this. You know, this is the only DOSCAR file you have here. See here. This is I already mentioned this before, but as you can see here is the highest value of density states, the lowest value of density of states, and in the energy range, and this is the Fermi level. You see. So if you go, let's see what is the density of states around the Fermi level. 0.58, minus 0.58. So more or less here, you see, in this region. As you can see, the density of the states is 0 in that region. So it means that the system has an effective band gap. See? So it's very interesting, right? Okay, so now let's visualize this just to be. So you can check from this. So I'm going to you can get this, by the way. We already did this in the section of the silicon, so you can go here. You don't have to repeat everything here. So let's do this. What is the density here? You see. So where I'm going to copy from this section, please. Section 5. I'm going to copy this density. Please plot density. This one, you know, the one we generated for the bulk. I'm going to copy this. And I'm going to paste it here. Here, repeat again. I take from part 5 the silicon crystal using PVE. I'm going to copy this. You remember this? So I'm going to copy this. And I'm going to paste it here. Here this is exactly the same. Only the plot range, I'm going to put plot range all. Okay. And image size, let me see, plot. Okay, so I think it is fine, this. Okay, I think I'm going to put image size 400, and this is 50. I'm going to put it 15, right? Let me check this. I think, yeah, 18. Yes, 1800. It's fine. The only thing is fine. Yeah, I can do like this. It's fine like this. There it is. That is the density of states. Okay, I'm going to pause this here just to repeat what I did here. Okay, so let's analyze around the Fermi level, please. So I'm going to go just to copy this part, and the plot range, I'm going to check this. In the sector B all, I'm going to put like this. From minus 3.5 to 1.8, comma, oh. Look this, okay? So here we can see clearly the material is insulator, okay? It is a small, has a small band gap, say that 0 point, how much is the band gap? More or less of, let me see. So more or less, just an approximation, right? So this minus EF. So it's around 0.25. My band gap is around, okay, band gap more or less 0.25. Okay. So this is, the experimentally is, I think is around 0.8 electron volts, but it's not, it's not a battery, and it's fundamentally correct solution because the silicon surface it presents a band gap. How do I know this? It's because of this. If you see the experiments, please, of SPS experiments, the scan improved microscopy experiments can be compared directly with the essential states. As you can see here, there are some features that we can check. See, so here is the band gap. As you can see here, the signal becomes almost zero in the region, right? And there is a peak here. So this peak is related to this peak that we checked. See, if there is a second peak here, so will be somewhere here. Of course, because there is an experiment, this is a surface property. That's the reason why it is roughly, And here there is also, you see this peak, more or less it represented here. So here, this shows that here is here, this peak here will be on here, right? Of course, in the experiments, this is a little bit wider. This band gap is a little bit wider, but it's fundamentally correct. See? So there is any better way to improve this, Well, how? It's because we have to use a more an improved version of TNT, like using a HABRU, or better to use hybrid functions to get the correct band gap, and we can directly match the experiment with the memory. So you see, so as you can see, the structure we computed really start to suggest that should be the correct structure because it can explain properly the experiments. But there is an even more nicer way to check this, and that is to check, for instance, the STM images. So I'm going to teach you how to generate these STM images. Okay, so we are going to train this. So that will be the last calculation we have in this training. Okay, so please check that you have this in the main directory in the sorry, in this directory of the that we are working here, right here. Check that you have this, please. You have this STM. So check that you have this file, stm.sh. If you don't have it, please download from the email. So because I sent it way before the class, before the lecture, I sent it this email, this file, this script. And please, if it's not black, convert it to black with CH mode. So if it's not executable, you have to enter that like this CH mode, right? 755 and STM.sh. So with this, we transform a common file to execute. Okay? So if you do an ls in your Linux and it does not show green, it means it is not executable yet. So you can create an executable with this. Okay. So open up this STM. It is mentioned, it's described in the manual, but I'll show you here. So part 8. What is STM? Here it is. My STM here. Here it is. You see? So there it is. There it is. Okay. So in my case, I'm going to change the course to, I think in the RX, I was using 4 cores. Let me check. In my RX, the last previous configuration, I used 4 cores, so I'm going to use the same as before. I'm going to do this. Okay. Check also that in your surface, see, folder, you do ls wave ls minus lh. You have that the file has some bytes, is not empty file. In the sur folder, you go to the inside sur folder, you have to have wavecard. Even that it might appear in your directory, please check that has some memory inside. I mean, that is not an empty file because that was the wavecard was computed in the last calculation of the after relaxation of something. So basically, what we are going to do is to project that states of the wavecard within our energy range and to check what happened in the vacuum. So that is the reason why, and this is the way that we are going to compute the STM images. Okay. So that's it. So let's do this, please. So please go back to this. We're going to run this script, please. Check that you have this. In my case, I have like this. In your case, maybe you need just only this course, this line here, and the rest is the same. So then we are going to have important file is a par charge -surf. The surface is 2x2 L5V10 .vasp. Why? Because with this file will be open in Vestandes, and the calculation will take maybe a couple of seconds. Okay, so I'm going to save it, and I'm going to run it. Yes. Okay, I'm going to pause this here. So I'm going to see, let's see what is inside of this file. As I mentioned, the part charge is. This is, in case it is doing this, let me see this STM here. You see, it's using this incar-STM. So what is inside of the incar-STM is here. So let me see. Look this. What it's doing is going to repeat the same calculation, but it's going to keep, the wavecard. Basically, it's going to use the wavecard already computed. And in this case, it's going to project the Concha wave functions in and inside of this range of energy, or minus 2.0 to 0 with respect to the Fermi level. Okay, so it means that it's going to integrate all the states that are between the Fermi level here, from here till -2 electron volts, right? So it's going to integrate it's going to take all the states and to project the real space from these negative means occupied states. If I do positive, would be from the Fermi level upwards. So here I'm going to use negative, only negative, and from this Fermi level till -2 electron volts. Why we are doing -2 electron volts? Because in the experiments, the experiment we have here, the image we have in the model, yeah, it was made with a bias here. It was made with a bias of -2 volts. Yeah. Where is this? So the bias is around -1.6 volts. Okay. So what we're going to do here with -2 volts to convert easily. Okay. So we have to minus means that is the integration of this we are mapping the occupied states. So mapping the occupied state means that we want to see what happens from the Fermi level to -2, in this case, -2 electron volts. We're going to pair with -2. Okay, so we want to see what is this pattern here, right? So we can explain this. Okay, so let's do this, please. So let's check this part chart file, please. Where is the part chart file? Here. So I'm going to open this file. Chart. I'm going to open it just with Xedit, and look this. Has this configuration, all right? And look this, after the coordinates of this structure here, this, by the way, this structure, it has the initial structure was the optimal structure of my slab. So in case here it is, the STM is telling you from which structure we should start this. This of course has to be the optimal structure, right? So this.
So we use the optimal structure of this. We copy the Concar file of the last Concar file we relaxed to Postcard, so it means that this. And after this, we have a grid 80 by 80 by 168. What is this grid? 18x, 18y, and 168 divisions in Z. So this is a grid, and this is the values of the partial of the charge that is integrated from the Fermi level to -2 electron volts. Okay, so we want to visualize this and to see it, to understand this. Okay, so to open this, we have a we have a strict program that can read this. So we are going to open with this with Vesta. Please open this with Vesta, and let's see what is this. Where is the part? My part charge is here. I'm going to open this with Vesta, please, and see what happens. There it is. Okay, I'm going to pause here till everyone has. Just open it, please. So once you have this structure uploaded, please just check here on show sections, show ISO volumes, and just we are going to I think it's in edit. No, in edit, you put lattice planes, please. In edit, go to edit, lattice planes, and you're going to put here a new, and you're going to put here 001. So we are going to make a plane 001 at 11 angstroms of height. Okay. Check this and look this. It is mentioned here, by the way. So just if you don't know what is this image that we're going to generate, it is the options are here, by the way. It's mentioned here. You see? You create this image 2 by 2. Yeah, we have to make a 2 by 2 at 11 angstroms. So this is the 11 angstroms here. What is this? See? It's here is 11 angstroms here. So you put here 11, distance from the origin, 11 angstroms. And you put OK, please. Okay. Now, we're going to boundary, please. And you're going to put 2 by 2. Here, 2 here. Only in X and Y, 2 times. No in Z. In Z, it doesn't make sense any periodic repetition. And you put OK. Now we have to fix the colors. You went to properties, you went to sections. Please check here in absolute values. Yeah, absolute values. And put the maximum is 3 times 10 to the 3 times 10 to the -6. The maximum value. What is this? Here, see? Maximum is 3 times E minus, how much I say? 10 -6. That's it. Okay, that's it. Everyone take here, please. I'm going to pause a moment here. Once you open this file in Vesta, please check this. Show section and show isosurface. I don't want to see section and isosurface. That's it. So it looks like there is no data here. Okay. Next, go to edit. Right? Go to edit. And you're going to check lattice planes. Right? Now you put new, so you are going to create a surface, and you're going to put the index Miller will be 0. I want a surface, a Z surface, that is perpendicular to Z. So will be 0, 0, 1, and you have to give the distance of this surface with respect to origin will be 11. Okay, and after that you put OK. Okay. Next, we want to do the boundary, please. So the boundary, here, you're going to check boundary, and you're going to replicate this 2 times in X, 2 times in Y. And you put apply. Don't forget to put apply. There it is. Okay. And now we have to give the color to correct the colors, right? So you go to properties, please. In properties, we are going to put the sections here, the last part here, sections. And after you put absolute tick, we're going to put absolute values. And after this, you're going to change this maximum value not to this value, but to 3 times 3e to the minus 6. And you put OK. And that's it. Since I want to see only the surface atoms, please, I want to cut all the atoms but the surface atoms. So how to do this? Press here the A, so just to change the point of view to A, so side view. And after check this, please, this icon here, the white arrow here. You see, I check on this white arrow. Now you can select atoms. I'm going to select atoms, all the atoms except those ones. So these ones that are here are the surface atoms. I'm going to delete this, and that's it. Now press C again, and now you're going to have this. Okay, I'm going to erase this also. There it is. So here you can see what are the atoms. I mean, the red spots, that is the highest intensity of the current, let's say, it is above this atom. Where is this atom, please? You can check this, please. You check, go back to this, and you can check this. See? The highest atom is on top of this, I'm going to put C again, please. I'm going to go this, see? The highest atom is around this topmost atom, you see this. So this atom here, you see, it is here, you see? It is this one. It is close to the, you see? So this buckling surface of silicon, the bright spots is just on top of the atoms that protrude more in the vacuum. See? Therefore, I'm going to put this to the top view only. You see? So these bright positions are where the atoms are more protruding in the vacuum. Okay? And that's it. So let's save it, please, this image for you. File, export raster image. I'm going to export this. So I'm going to export like this, PNG, and that's it. Save it. I'm going to let background transparent and okay, and that's it. We have saved this file. Okay, so I'm going to start generation. Of SD images for silicon 0.1 and 00 iPhone 2x2. Okay, this will be a subsection, please. Okay, so first of all, we have to import the bar chart. These files, right? Bar charts. So let's import. So I'm going to put in is equal to import surf bar chart this PNG dot BASP. This dot BASP, that is the actual file, comma, okay. This first, okay. So then if you open this, so let me check this. I'm going to side by side just to explain you what I'm doing here. I'm going to open side by side this file as a text vid. So you see, I need to, first of all, to inform how many atoms I have. So I have to add 20 plus 8. So instead to do this, I have to use num at is equal to plus in 7. So it's 28, right? The number of atoms. Now the lattice You need the lattice is in the input file is from 3 to 5. That's my lattice parameters, right? Now, the file that I'm going to use to do the S in images is from here, from these values, see? I'm going to use these values of this. From this value and below, and all these values over here, I'm going to, okay? So we have to, I'm going to do the STM, values of STM is equal to this. In from 7 plus number of button plus 4. And the last one will be minus 1. Okay? And this will be flattened. Okay? So let me see if we are fine. You have to have these dimensions. So that is the around, this is the dimensions you should get. Everyone has to have exactly the same value. More than 1 million data points. Just to check this, please, STM, let's put 1. The first value has to be around this, not exactly the same for everyone, but you should have something similar. 0.5 something you have to have, 0.50 something, right? And let's see the STM, the last one, just to check the checking point. This will be something like this. Everyone has to have roughly the same. Okay. I'm going to pause here. Now we have to define the divisions along X and Y, basically, right? So the divisions along X and Y is 80 and 80, right? So why I'm doing this because I have to do I have to use a periodicity of this data because so therefore the divisions in X is this in 7 plus not plus 3 comma 1. That is division. Next, the divisions in Y is equal to this, but plus 4, right? Divisions in Y will be this plus, plus 3, comma 2, the second one. And that's it. And the Z range, now also I need this, the range along Z will be this in the 5, the P vector is 2, comma 3. So that is the range in it means that the length of my lattice vector in the Z. See this value here, right? It's from 0 to 16.46. Okay. Now I have to transform the data. I will explain this later in a moment. I'm going to transform data in such a way that I can apply periodic boundary conditions. Okay, so this is equal to this. I'm going to start with this. This is equal to this. Parentheses. I'm going to put like this. Hashtag, right? And after like this. Partition. Comma. Div next. And now partition. Div in Y. Partitions in Y. And now map append first hashtag third finally, transpose. Transpose. Then I'm going to put like this and look. Okay, this is the transform data. I'm going to pause this in a moment here. I'm going to explain very quickly what is doing this script, these lines here. This. So basically, we want to process this data here. But look this data is separated by only there is 10 columns and so on, right? But what is doing this, in fact, is doing this. We have 80 values from here to here. You see? The 81 is here, and so on. So we will say to 640 will be the last value in the same plane, right? So 641 will be this point here, and so on. So the arrangement of data is like this, but they put it, by default in this, in the Fortran code they use, they arrange data like this. But in Mathematica, you have to give a structure of this. You have to tell, okay, if the first 80 will be the first line, the next will be the next, and so on. You part from the 640 values that will be here, will be right here, but we have periodic boundary conditions. It means that you have to complete the data because I does not complete the data. You have to add these extra values. Why you have to add these extra values? Because we have periodic boundary conditions. In that case, but that's why I'm doing this? Because this value here and this value here has to be exactly the same. If you don't have this exactly the same, we cannot apply this. I'm going to show you in a moment. In the Mathematica, you can apply this periodicity, so you can split or you can plot functions, in as many times as the ratio one, right? So that's the reason why we do this. So basically, in this script, what I'm completing this amount of data here, this is a wall of data here, see, and a wall of data. So in that case, in such a way that this wall of data, this part here is exactly the distance here. This wall of data here will be, see, in this direction will be exactly this. So this data we're going to complete, okay? So if we do this, you do shift enter and you have this. This is only, remember, it's a function transform data. So we have to do, I'm going to put STM1, the data that I'm going to plot with the structure mathematical understanding will be this. STM transform data. There it is. Let me see. Right now STM 1,1, the first value have this. See? Let me see the STM1 dimensions. See? You see, now it's 81 times 81, right? Times the same value in Z, and Z doesn't change. Why? Because now we complete these values to make it an exactly periodic arrangement of data, and that's it. So we are okay. So here I'm going to put here the interpolation. So we're going to interpolate for STM1 data. STM1. We're going to interpolate. So I'm going to put the interpolation. So right now we're going to interpolate using periodic conditions. So I'm going to put list interpolation, right? Hashtag, comma. In X is 0 point, you have to give the ranges. In X is from 0 to the lattice parameter A, that is 3,1, right? Next is comma, from 0, comma to the in 4, 2. finally, and that's it, because, well, in Z also you have to give the range 0, in 5, 3. So I give so I need to scale this to the actual lattice parameters, right? So I have this, comma, and after that, periodic interpolation, yes, that is important, periodic interpolation. So I'm going to put true, no, true, or false, because in Z I don't want periodicity. There is my, sorry, yes, it's correct. So I'm going to put STM interpolation is equal to STM1, this, the interpolation. There it is. So let's check this. Let me see the interpolation. Now we have a function, a 3D function in any part of the space, 0,3, you see? So that is approximately the value of my data now interpolated inside of this region 0,3. So for the coordinate 0,3, we have this value. I'm going to pause this here, please. Okay, so now I'm going to start to visualize this interpolation in 3D of this data, right? So I'm going to put this. So here I'm going to do a 2 by 2 extension of my data in X and Y. Later we're going to play with more extensions, doesn't matter. X goes from 0, so there is, to nx multiplied by the lattice. Y will be from 0, ny times the lattice to comma. Now z, I will explain this. Z I'm going to take from 8.6, so it will be in the back, you see, comma 11.6. Just in case, from okay, where did I get this value? So if you open this, let me see this surface. I'm going to show you this. The concave one. I'm going to open the concave one, this one. This is the optimal structure. Look this. The topmost atom is here. See this fine. It is above 6.59, right? So basically, I want to see what happened in this region that is 8.6. So around this region, you see, around this region, I want to see from 8.6 till 11.6. I want to see this. See. So it means this is around 5.6.6. So I said 2 angstroms above the topmost atoms till plus 3 angstroms more. So that region I'm going to check. That's the reason I take this. Always STM is above, the surface atoms, well above, the experimental is known that it's about 10 angstroms, but in this case only I'm going to use this. Okay, comma. And now let's do this color function. I'm going to put this function. We're going to use this x, y, z, f, color data. I'm going to put sunset colors. Of Z. So what I'm going to plot is along Z, the colors, the colors that is going to, it's going to put colors in along Z direction. Plot points. We always use plot points a small amount of points to use it only 30. Max recursions. I'm going to put 0 to speed up the plot. Now box radius is important to give, the correct relationship in the radius. Box radius will be like this. You have to do 1, so the x will be my the x will be my reference, 2 divided by, you see that there's only this ratio is the same, divided by nx multiplied by the lattice. Like this. And then C, I'm going to put this minus this value divided by the same. So this is the way that how I do proportional to the actual, we make it the same proportions. Scale to the cabinets, from axis level, I'm going to put like this, X in angstroms, comma, Y in angstroms. How to put angstroms is escape, A and G angstroms, comma none. Okay, comma, viewpoint. I'm going to put this to a completely top view. Escape in. How to put the infinity, okay, how to put angstroms here, but what I'm using. So angstroms is escape and escape. Infinite is escape in escape. See? Armstrong's infinity. What else? Comma. Base style, the same we used before. So I'm going to copy this base style we use here, please. Not this one. I'm going to copy this, please, here. The previous plot. Base style Helvetica, and I'm going to put font size only 13. What else? A contour style. I'm going to put directive. Opacity. So later you can play with it. And finally, lighting, ambient light. Gray level. Comma. Mesh node. And that's it. Let me see. Don't forget to save it before you run it. You save it, please, just in case you feel something. Otherwise, it will crash this. Let me see if this everything working fine. Okay. There it is. It's working. Okay, I'm going to pause this here so you can copy everything here. Okay, so this is a 3D image, as you can see here. What does it mean? This surface is in 3D, as you can see. It means that this is the path it is following a tip in the experiments. So bright means is closer to the observer, see? So if you're here, the observer is, so it means that tip is closer to the observer. Dark means it's far away from the observer. So this 3D image is produced, you know, the data in the real STMS experiments, they get 3D data and they plot it. But from the experiments, they cannot tell exactly where the atoms are. But we know that the brightest spots here are in the atoms, the silicon atoms that protrude more to the vacuum. And that's it. Okay. I'm going to pause this here, please.